Hello everyone. We're going to continue with section 6.4. Hopefully you have already gotten some practice with drawing both orbital diagrams and electron configurations, such as the one we're showing at the top here. What we're going to add here is some discussion around additional ways to shorten this up and how this, in more detail, how this relates to the periodic table. So as you've practiced this, you've probably noticed that it takes a lot of kind of tedious writing to do the orbital diagram, and maybe a little bit less for the electron configuration. However, it is still a little bit tedious because it always kind of starts out the same way. And it turns out the really interesting parts are not the start, but kind of towards the end. As you start to get to larger atoms with, maybe 30, 40 or more electrons in them, even this method becomes a little bit tedious. It turns out that, and hopefully this will make sense, the electrons that are the most important in terms of the way they affect the properties of the element are the outermost electron shell. We call these valence electrons. Okay, so you'll hear the term valence electrons quite a bit, kind of from here on out, and potentially even in some of your other courses such as biology. So valence electrons are the electrons in the outermost energy level or outermost shell. So the ones with the highest quantum number, principal quantum number. The other electrons are what we call the core electrons. So the core electrons are any electrons that don't have the highest principal quantum number. So there's an example here with sodium. So we're showing the electron configuration for sodium, and we notice there is a 1, a 2, a 2, and a 3 for the principal quantum number. So the valence electrons are the ones that have principal quantum number of 3. So those are the 3s electrons, and there's one 3s electron. The rest of those are all core electrons. They have a lower principal quantum number than 3. So what we often do to abbreviate larger atoms is we take all of the core electrons and we represent those as a noble gas. And it's not just any noble gas, as we'll see. There's a reason why we do that. So here we're showing the abbreviation for sodium. We write the symbol for neon in brackets here, and then we have the valence electrons come after that. So this is sometimes called the condensed electron configuration. And so it's showing only the valence electrons, and then we have this abbreviation for everything else. So the question we might have is, how do we know which noble gas to use for the abbreviation? To answer that question, I'm going to go back up to this periodic table we looked at earlier. There's another periodic table that does a good job of this, but I want to go back to this one for now. So on this table, what you'll notice is that the noble gases are, of course, all over here. And so the noble gases end with P6. Every one of the noble gases ends with a P6. So 2P6, 3P6, 4P6, etc. So when you get to the noble gas, you have filled that electron subshell. You filled everything that is there. Okay. So that is when you know when to do that abbreviation. So let's go back to where we were. So we see it ends in 2p6, so those are core electrons. When you have a noble gas, you have all of those core electrons are full. And so anything after that is where you write the valence electrons. Okay, so that's how you know how to select the noble gas for that abbreviation. So there's some additional discussion of that in here. Um, here's another periodic table. So let's go ahead and look at this one. This periodic table will be fine to use as you are kind of learning some of these ideas. And I want to point out a few things about it. Um, First of all, I say it's fine to use as you're learning these ideas. When you are taking the exam, you will not have a periodic table that has the orbital diagrams information on it or the electron configuration information on it. You will need to know how to figure that out, and it's pretty straightforward for the most part. But I did want to point out a few things on this periodic table. There are some exceptions, and I think when we talked about the learning objectives, I said you didn't need to know the exceptions, and that's true, but you do need to know that they exist. And the reason for that is if you are practicing some electron configurations and then you're checking your work, what you'll notice is that it's not always what you thought it would be. So two of the main ones, I'll go ahead and point them out. On the in the 3D section, we have chromium. We go 4s2 3d3, and then we go 4s1 3d5. Okay, so that's an exception. And then copper, so we have 4s2 3d8, then 4s1 3d10. So what we're doing there is we're either half filling or completely filling the D subshell before we are filling the S. So we kind of jump back and forth between those. And there's a few more, there's even more as you go down, especially when you get to the F's. You have three things you're trying to balance there with S, D, and F being partially filled. You don't have to know those exceptions, but if you are writing an electron configuration and you come here to check your work and you see it's not what you thought, that's the reason why. Okay, so don't worry about that too much, and just kind of see, you could figure out what it should be, and then use that. Okay, so don't worry about the exceptions if you're checking your work here. So this is talking a bit more about adding the electrons. Again, we're going to skip over the details of the quantum numbers like L and M sub L. So don't worry too much about that for now. You can do this without having that information. And there's some examples here if you wanted a few more examples. Okay, so some of you may have already figured some of this out, but I want to kind of show you how the electron configurations lead to the periodic table. So we've already talked about that's true. Let's talk about how we know that's true and what that looks like. So when we initially introduced the periodic table, I just kind of told you and had you accept it as fact that within each group of the periodic table, we have similar properties. And not necessarily each group, but certain groups are very, very similar. So let's go ahead and discuss that a little bit in terms of how that relates to the electrons. So the valence shell, again, is the outermost shell of electrons, and that's where we have a lot of the chemistry actually taking place. So this is particularly true with the main groups or representative elements. So they could be called either one of those. So going back to our periodic table, again, what are the main groups? They are what we have here in blue and what we have here in red. What the main group elements have in common is that whichever electron was put into them last is always a valence electron. Always a valence electron. So what that means is, especially for main group elements, we have very similar properties all the way down. And in fact, that's why we have special names for some of them, right? Because we know all alkali metals will react in a certain way. All halogens will react in a certain way, because that valence electron determines so much about their chemical properties. Okay, So main group elements have very similar properties because their valence electrons within each group are identical. Especially true of this are the noble gases. Okay, so remember the property of the noble gases is they're non-reactive. Um, it turns out that you can sometimes get them to react if you try hard enough, but it's very difficult to do. And the reason for that is because their valence electron energy level is completely full. There's no room for additional electrons there. It turns out that that is a very stable situation, and we'll discuss this more as we get into the next module. But as you get close to that, so close to that would be, okay, you have almost a full valence shell here. I almost said 8 because it turns out that it will be 8 electrons. You're almost there here. So these ones want to try really hard to get over here. Okay. Likewise, you're almost there over here. You just kind of are going in the opposite direction. So these ones are trying really hard to get over here as well. They just have to do something different to get there. So you have very specific reactive properties for the halogens, also very specific reactive properties for the alkali metals. They just happen to be different, very specific properties. And as you get a little bit further from there, so alkaline earth metals, and then these groups over here, you do still have those similarities. They're just not quite as pronounced. Okay, so that's a bit of an explanation for what we see with the main group elements. Let's talk about some of the other regions as well. So with the transition metals, and we talked about this in the previous video, remember you're not adding a valence electron, you're adding less than a valence electron, right? So whatever your period is, you're adding one less than that, right? So here, so 3, 4, 5, 6, etc. Because of that, we have a lot of more variability than we do with the main group elements. So this is why for the transition metals, we often have cases where we can have, maybe a +2 or maybe a +3 or maybe a +1 or maybe a +2. So you have more variability here because you might be interacting with s electrons, you might be interacting with d electrons, you might be interacting with both, or you might be interacting with multiple combinations of s and d electrons. So there's a lot of variability for that reason. So those are the transition metals. And then we have what are sometimes called the inner transition metals. And these are also sometimes called the lanthanides and the actinides. Okay, so those elements are, again, the ones down here in green. And so what's happening here is they are adding not one level below, but 2 levels below. What that means is that for these, and these are something that are not studied by a lot of people, so it's kind of very, very specialized to get into this kind of work. But there's less variability across the inner transition metals. In fact, they were once called the rare earth metals because they were so similar it was difficult to separate them from each other. And so people thought they were rare, but they weren't really rare. There's a lot of them. Or I shouldn't say a lot. There's no reason to think they're more rare than other elements of a similar size. I guess I should say. But they're very similar, so they're often hard to separate from each other. So we can see where things are in the periodic table affects their properties. So with those inner transitions, again, probably not something you need to know a whole lot about, but in case you're curious, that's some information about those. Okay, so based on where things are on the periodic table, we can see why they might have some of the chemical properties that they do. And those chemical properties are things we'll explore in more detail in an upcoming section of your book. And then finally, the last idea for this section is the electron configurations of ions. So when you have an ion, it will, of course, gaining or losing electrons. And so if it's a positive charge, you are losing electrons. So when it loses electrons, it will generally lose electrons in the same order that they were put in. Okay, so the last electron that you put in is the first electron to go out. That's for the main group elements. A little bit trickier for transition metals because they do that a little bit differently. They will lose their s electrons before they lose their d or their f electrons. So just be aware of that. There's some practice on that here. So I'd recommend looking at that practice before completing this module.